Well, hello, and welcome to an introduction to the Advanced Photonic and Electronic Devices concentration in the Department of Electrical and Computer Engineering at the University of Washington. Do you like to design circuits, make things, go hands-on? Is it fun to spend time in the lab, figure out how things work, get them to work, and walk out knowing that you've built something that does something? Are you thinking about going to graduate school? Want to go for a deep dive into how things work? Or do you just like to understand the way things work, all the way down to the tiniest of scales, from micro to nano, all the way down to the quantum level or the atomic level? Or do you just like to work with systems from start to finish? That's what drew me into electrical engineering and the world of devices. Devices knowledge gives us the opportunity to work on everything from the very beginning to where we collect information to where we turn it into something useful for society. But why are devices really relevant in today's computer engineering and electrical engineering disciplines? Well, if we start with the basics, without this little device here, which wasn't so little in 1947 when it was invented by researchers from Bell Labs, we would have no embedded systems or computer science. This is the bipolar junction transistor, the very first one, built a long time before you or I were born, but it started the way and paved the way for the semiconductor revolution, which has brought us not only personal computers, but tablets, smartphones, and a huge variety of consumer electronic devices and other devices that now serve society in ways that we could have never imagined when this first transistor was demonstrated almost 100 years ago. Looking into the future, devices are also important to support what we call the grand challenges of engineering. And the National Academy of Engineering in the United States has defined 14 challenges that are critical to the survival of civilization and the improvement of society through the 21st century. 3 of these challenges are shown here and depend heavily on devices. 1. Engineering the tools of scientific discovery will allow us to understand the many unanswered questions of nature and will fundamentally require an interface with the inherently analog world. Sensors, actuators, and other devices are absolutely essential to understanding better the planet we live on and the way it is evolving to support or not support us, depending on how we manage our natural resources over the long haul. Engineering better medicines is particularly important in this day and age as we face the COVID epidemic. Good engineering can enable us to get to the root of these viruses much more quickly, understand how they work, go in and provide drugs that can sense where they need to be and what they need to do when they get there, and deliver vaccines and other tests that provide health care directly to each person. And in the power systems area, as we continue to move away from fossil fuels, devices are also essential to the development of renewable energy sources such as solar energy. Photovoltaic cells are one of the very fundamental devices that we discuss in this area of concentration, and they're essential to the many solar panels and ways of converting solar energy to useful electrical energy around the world today. And if that doesn't make devices interesting and essential enough, the fact is that Moore's Law, which has continued to guarantee that the capacity and speed of computers will double around every 18 months to 2 years, is now starting to die on us. Devices simply can't get any smaller and still operate more quickly. And as transistors continue to try to get smaller, or delve into different architectures to ensure that they'll continue to deliver the speed that we need for all the applications and embedded systems program we do, we're going to need another device. And understanding how to make transistors smaller or different so that they deliver that speed and capacity over the long haul requires a fundamental understanding of how they work, which is available in the advanced devices concentration. But more than that, if we move away from Moore's Law and the continued hunger for speed, we can also look at what's called the Internet of Things, that continues to diversify how we use devices and how we create computers and where we integrate them. And the Internet of Things will not only provide us a huge variety of electronic and consumer electronic devices moving forward, the Internet of Things is also essential to delivering on the grand challenges we just looked at in the previous slide. As the bottom line, the Internet of Things continues to grow, with an expectation that this year it will surpass $50 billion globally. And as we continue to put devices and embedded systems in more and more things and connect them wirelessly, that level of communication and networking will give us the ability to serve society and provide solutions to major global problems in ways that we've never had before. But fundamentally, the Internet of Things has to interface with the rest of the world. And in order to do that, we'll need devices, and we'll need a good understanding of how these devices work. Because as we move out into the world and monitor this, that, and the other thing that's relevant to the survival of civilization, we'll need to do that on a minimum of battery power, and certainly without much access to AC outlets. So within the bachelor's degree, the Advanced Electronic and Photonic Devices concentration can either be taken alone as your main area of interest, or it can supplement another concentration, providing a deeper dive into the devices that support that concentration. For example, in embedded systems, we can support embedded systems by looking more deeply into how semiconductors work, how solar cells work, how a wide variety of sensors work, and how the next generation of transistors may or may not provide the capability that we've gotten used to with Moore's Law. In the big picture, this concentration area doesn't require a lot of credits, 25 to 29 credits depending on which capstone you choose. And the courses along the way, especially at the 400 level, provide an insight into devices and a broad overview not only of how those devices work, but of the many possibilities out there of devices that can support other systems. What's important to know with devices is that adding an interest and curriculum in devices to your resume can give you the ability to get a salary increase coming out of the starting gate when you graduate from the University of Washington. While starting electrical engineers earn a salary of about $65,000 to $71,000, adding devices to your area of expertise can provide you the ability to make $20,000 or $30,000 more, even at a starting salary. For example, applications engineers for the Internet of Things make between $105,000 and $178,000 in their career. This is quite a bit higher than the average electrical engineer's salary. So devices in and of themselves, because you just have to know how things work, or because you love to build things, or as an add-on to other areas of concentration, makes a lot of sense for the electrical engineering student in providing a resume that's diversified and enhancing the options that you have for a job that starts either as an internship or once you graduate from the department at the University of Washington.